Okay, so the difference in the color is mainly the wavelength of the light that is being emitted by those specific diodes. And there's another thing that is different about these LEDs is their threshold voltages or turn on voltages. So for example, for a red LED, the voltage is around 2.2 volts. However, for green and blue, it is a little bit higher than that. So for blue, it's about 3.5 to 4 volts, and for a green LED, it is going to be between 2.2 and 4 volts. So a little bit higher than the red one. And red one is most commonly used just because it is convenient to get it, and it is a easily detectable color. um, Now, one common thing that gets could be confusing is that it is inside, it's just white light, but the plastic casing makes it appear as red, green and yellow. It's not the case. So the plastic casing is just for the user to understand that it is red, green and yellow when the light is off. However, if these were clear casings, you would still see red, green and yellow respectively. And they essentially work on the principle that if you have a voltage that you are applying across the two ends of the LED in the forward biased region, then a normal diode such as a 1N4148 diode would simply allow current to pass through it. However, a light emitting diode will emit light when we go above 2.2 volts, for example, for the red LED. Now, the question, a more important question is it safe to simply connect a voltage source to an LED? The answer to that is no, it is not particularly safe to do that. And let's talk about why. So I'm going to write something over here, and so that we can talk about why uh, that is not the case. So I'm going to leave some space. I'm going to put a voltage source here, going to put a resistor here, and I'm going to put some LED over here. And the LED symbol is two arrows that are going out indicating that light is being emitted. And then suppose this is ground, this is my resistor R. I don't know what R is. This is my Vin. Let's say this is my red LED. Doesn't really matter. But if you see here, as you connect this circuit, and because you have connected it in such a way that the positive voltages of Vin will make this LED be in forward biased region, and if that is the case, then some current, say I LED, will flow through it. So now the question is, if this resistor wasn't there, what would happen? Well, if the resistor wasn't there and I would be connecting this to a LED directly, then if I increase this voltage to a high value, then that will damage the LED. So in order to protect that LED, I'm going to place this resistor in series with it, so that there is essentially a voltage divider that is happening between the resistor and the LED. And the resistor is also functioning as our current sensing resistor. So that's going to allow us to measure how much current will be flowing through it. And so what should you do? How should you choose this R? How should you choose it? Is any R going to be okay? Well, that depends on how much current you want to flow through. So in order for the light emitting diode to have a reasonable intensity of light that it emits, about 20 milliamps is what is desirable as the current that flows through it. So if I want 20 milliamps to flow through the LED, that information will help me figure out what resistor to choose. So simply I know that Vin is going to be, if I apply the Kirchhoff's voltage law on this, Vin is simply going to be VR plus VLED. The input voltage will be split up between the resistor and the LED. And I know that VR, voltage across the resistor, is simply going to be I LED multiplied by the value of the resistor R. So if I rearrange this, I get to an equation that you see on your screen. R equals V in minus V LED divided by I LED. So I will choose the resistor R in such a way that the current is about 20 milliamps. So that's essentially what this is for. It is to choose an appropriate value for R depending on what colored LED you have in the circuit. Okay, so let's go back to the LED picture here. Those are the three that I'm showing here. Next, we will talk about photodiodes. Photodiodes, we are not using it in EI, but I happen to have a photodiode in my part, so I'm just showing it to you. The difference it is a black plastic case on top instead of a colorful one. That's a photodiode. So this essentially detects light. So if light falls on it, it will allow current to pass through it. But photodiodes are slightly different from LEDs. LEDs function in the forward biased region, but photodiodes function in the reverse biased region. So negative current, negative voltage. That is written up uh, in the write-up. So I encourage you guys to read that. However, photodiodes are not a part of this course. Instead, we are going to look at phototransistors. Phototransistors have an advantage over photodiodes. Photodiodes, usually the current is very small. For phototransistors, because we can operate a transistor in the active region, we saw that in experiment 8, we can function very close to 0.7 volts for the turn on, or sorry, between the base and the emitter, around 0.7 volts, which is where it is going to be in the active region. And if it is in the active region, then it functions as a current amplifier. So whatever current that flows into the base terminal of the transistor, the collector emitter terminal current will be 170 times of that. So because we can get a much larger value of the current by using phototransistors, we will use phototransistors because they are very sensitive to light. Photodiodes are not that sensitive to light because they don't have that amplification aspect to it. And we are going to be using phototransistors, and you can see this is the component in it should be, if you have your parts kit from EI, this will be there in it. It will have a clear plastic casing. Now there is one thing, if you are doing this at home, I want to make you aware of the terminals, because we are calling this a phototransistor. Where is the emitter, where is the base, where is the collector? So the base, in a transistor we apply the base voltage to control whether the transistor is on or not. Over here, our light that falls on it is going to dictate whether the transistor is on or not. So light is essentially the base of the transistor. And there should be two left, right? Collector and emitter. Where is the collector and emitter? Well, for that you have to look at the phototransistor from the top. And if you notice, well, it might be very difficult to notice, but I'm going to try. If you zoom in all the way, and that's the highest I can go, there is, on the plastic casing, there is a flat edge on this side. Very difficult to see, so you have to pay attention. You have to look at it from the top and notice around that circular disc, there is a slight flatness to it. And that flat side is essentially the collector of the phototransistor. So this one is the collector, and of course the other one, emitter, is the one that is on the other side. So that's how we know the base, collector, and emitter terminals of the phototransistor. Zoom out over here. That information is crucial when we start putting this in the circuit, which is why I thought I would talk about that. So that's your phototransistor. This is the photocurrent versus the radiant incidence graph obtained from the data sheet of the phototransistor. On the x-axis you have the intensity of the light, radiant incidence, and on the y-axis you have photocurrent in milliamps. They are both plotted on a log scale. So it's linear on a log scale, which means that even if they were linear in the linear scale, there would be a linear relationship between them. So as you are increasing the light that falls on the LED, or on the phototransistor, the amount of current that flows through it will increase. You can actually do this at home using a calibrated iPhone, for example. If you have played around with the iPhone flashlight, you know that you can increase the intensity of the light in steps of 1, 2, 3, 4, for example. So that way you can explore 4 different points on this graph by doing that. But you have to be a little bit careful in your experimental setup, because you don't want the phototransistor to be overwhelmed by the flashlight. So you may have to use some sort of a cloth to reduce the intensity, but still go up linearly in terms of light intensity. So those are some ideas if you want to play around with that. But today we are going to be focusing on an LED that we are going to couple with the phototransistor here. Let's move on to talk about the next one. Well, the next one is 1N4148. We have been doing the experiments using this. This is the small signal diode, which is used for the fast switching application. There is another diode next. It is the Zener diode. We are going to talk about the Zener diode. Specifically, it is the 1N751 as the part number. That is going to be used as a voltage regulator. We'll talk about that in the next class. And then we talked about the photodiode right here with the black casing. Okay, so I think that's a quick sort of review of the various types of diodes that we have been looking at. All right, so what I'm going to do is preserve the phototransistor. I'm going to scroll down to the experiment that I need to do right here. I'm going to push this by the side. So things are going to get interesting now. Alright, so what I have in front of you are two circuits. One has the red LED, and the other I'm going to place the phototransistor with the collector going up towards the resistor. And I'm connecting them in such a way that they are nose to nose, meaning that in order for the light to couple very well between the red LED and the phototransistor, I have essentially turned the leads of both of them such that they point towards each other. And I have placed my optical transmitter on the board on the left, and I have placed my optical receiver on the board on the right. So as you can see, there are two boards that are disconnected right now. So essentially, if you look at figure C-2, there is a LED on one board, the one on the left, and there's a phototransistor on the board that is on the right. And the only coupling between them is the red LED. So the light is the one that is going to connect between them. I have a resistor, 330 ohm resistor there to protect the LED, which is also going to function as my current sensing resistor. There's a phototransistor over here where I'm measuring the voltage between the collector and the emitter junction of the phototransistor. Now, let's talk about what we expect. So, if there is light, then the collector and emitter terminals will be connected, and on the output, you should measure almost 0 volts, very close to 0, when there is light. When there is no light, then there is collector and emitter are open circuit, which means that now you will be measuring voltage very, very high, so very close to plus 5 volts. So when there is light, you measure 0. When there is no light, you measure 5 volts. So that's exactly how we are going to expect this to work. So let us see if we can set this up using WaveGen. The first thing I'm going to do is to connect the yellow wire to my optical transmitter side, so that's the yellow wire on the left. Next, I have a 330 ohm resistor connected here, which is orange, orange, brown, to the red LED, and the other end of the red LED is connected to white wire, which is our negative power supply that helps us to increase the range of voltages over which we can operate this experiment on. I also have two orange wires for channel 1. So let me connect them now. So I have orange connecting to wave gen, and the other one is going to be orange stripe. I had it connected to ground. I need to change that and connect it to white wire here. White also goes to analog discovery. I'm going to put that to -5 in just a minute. What else? So my transmitter connections are done. On my receiver I need V plus, so positive power supply needs to be connected. Next thing is blue needs to connect to blue for channel 2, and the last thing is ground. So ground and blue stripe are connected together. um, in this case I have blue stripe connected to ground external to the board. Alright, so I believe I have made all the connections here, and if not we'll find out. Let's see. So in a moment here, in order to get a really good coupling of light, I'm going to switch off all the lights in the room so that there's no ambient light, and then we'll start the experiment. So things are going to get dark. Please don't be alarmed. Well, so that's that, and maybe I can switch off this. And I will switch off this light as well. Everything is dark. So now I'm going to go to WaveGen. I also need supplies, so I'm going to turn on supplies here. Red connected to +5, go all the way, +5, done. White connected to -5, all the way, done. And then I can keep them ready. I'm going to go to WaveGen, give that a square wave because that's what the write-up asks you to do, square wave. Let's see, what is so if I look at the write-up here, let's see, it says function generator square wave 100 hertz 5 volts, and then V minus should also be 5 volts. Okay, so 5 volts, sure. So this is going to be set to 5, and I can turn that on, and I can turn the supplies on. And I hope you guys see that the red LED right now is actually blinking very fast, and in order to prove to you that it is blinking fast, I'm going to slow it down to say 5 hertz. And when I slow it down to 5 hertz, you can clearly see it blink at 5 times a second. Let me go back to 100 hertz here so that we can see it blink really fast. So now we are going to go to scope, turn on the scope. We are going to probably have to adjust a few things here. So for example, 2 milliseconds is probably okay. However, our range needs to be changed. So I'm going to change the volts per division on both channels. And if probably I need to also change the offset here so I can trigger it over there. Okay, so this particular plot tells us the story. So the orange one is basically controlling the LED. So when it is high, essentially we are sending light, and when it is low, we are not sending light. So when we do send light, we measure 0 on the output. When we don't send light, we measure high at the output. The only disadvantage that the phototransistor has when compared to a photodiode is that it responds to things a little bit slower. So it takes its time to go high and come back down. a photodiode does that switching relatively quickly. But yeah, that's it. So if I had ambient light, for example, I'm going to turn on the light and show you why I switched it off. So as you can see, if I the moment I turn on ambient light, everything gets like overwhelming for the phototransistor, and the output goes low the entire time. So as if it's on all the time. But I wanted to distinguish between my signal and the ambient light, which in this case is operating like noise. So when I switch that off, now you can see clearly that really good coupling between them. Um, and so how do people do this in the classroom? Well, in the classroom, there will be a signal. However, it will be a very very weak signal. So you will have to look at it at a very very small volts per division for the output. But over here, I don't need to look at it in two different scales on channel 1 and channel 2. I can look at it both of them on the same scale. Okay. And this is going to be sort of this particular concept of optical light transmission and reception is going to be part of project 4. We can transmit interesting things with light. So stay tuned for that. Okay. I guess in terms of the and I can do a few cool things here, right? Like I can um, put a barrier between them. So for example, if I put a pen in the middle, you see what happens right now. The phototransistor is not getting any light because I put a barrier in between. So it is saying that even though there's a little bit of light still squeaking through, but everything is high right now because it's not seeing any light. But if the moment I remove it, it comes back down. And just to give you a sense of how good the coupling is, you see, even if I move my transmitter and receiver far away from each other, I'm still able to couple the light very very well. And this can only happen with the ambient light being off. I can never do this in the classroom. All right. So I hope that was interesting to you. I'm going to move on to the next one if you guys don't have any questions. So I'll give you a moment to see if you have questions here. Yeah, if I misalign, I'll lose it. So for example, if I do that, you see, I just move down here, it will think that it's not getting any light. So if I move up or down, then I lose the signal. So I'll have to be nose to nose with respect to the LED and phototransistor. So if I was doing this in a real world scenario, I would need some sort of a device to uh, make sure that the coupling between the transmitter and the receiver is really good. So some sort of a lens that allows you to focus that light energy to a particular point. Okay, let me stop here. Um, oh, you guys might be interested in this, right? So let me take a MATLAB shot. MATLAB. So for example, I do file, export, save. So this is going to be figure C-2. Okay, so if there are no questions, we can move on to the next part. Actually, we will do a discussion on Zener Diode on Thursday, because this is sort of where I start for section 1. I want to keep you guys in sync. I will stop the recording here.